for those of you who completed the Chapter 6 test review on time. For those of you who didn't, let's make sure we can meet some deadlines. I'm going to go over the ones that I saw were a particular problem. There weren't many. You guys look like you had a pretty solid feel with the material. If there is something that I don't cover, please send me an email. I'll be more than happy to review any specific questions. Ahead and turn the webcam off to go ahead and work on our problem solving. Otherwise, you're going to be looking at my nose the whole time. All right, so we have this one. This was the one I saw the most issues with. So let's go ahead and get started. So we have a 1,300 kilogram car. That goes ahead and tells us that we have a mass. It's coasting on a horizontal road with a speed of 18 meters per second. After passing it over an unpaved sandy stretch of 25 meters long, the car's speed has decreased to 14 meters per second. The first question says, what was the network done on the car positive, negative, or zero? You only needed one word to find this, or one part of the sentence, and that's the car's speed decreased. If we have a decrease in speed, we're going to have less kinetic energy than we started with. Our final kinetic energy is smaller than our initial, so when we do that subtraction, we get a negative. So the net work done on the car is negative. Okay. The next part, we want to know what is the average net force on the car in this sandy section of road. So we want force. So we have initial and final energy, we have mass, and we have displacement. We know through some of the principles that we've talked about before, if we have a change in speed, we know that work is done. So we are looking at the fact that work is equal to a change in kinetic energy. We also know that work is equal to force times displacement. Right. So we're going to set these two terms equal to each other. So force times displacement is equal to that change in kinetic energy. Right. All right. Remember, it's always final minus initial. For ease of typing into my calculator, I'm actually going to take this 1/2 m in both terms and factor it to the front. Right. That just goes ahead and simplifies some of the math that we're going to do later. We're specifically interested in force, so we're going to divide both sides by our displacement. Right. If I want to make this super clean algebra just so that it looks nice, and you don't have to do this obviously, just something to let you know, this is going to look like this in terms of clean algebra. So you don't have to clean it up to that effect. That's just sort of an example. So now we can go ahead and plug in the numbers we have, because we have everything. We have our mass in kilograms, we have our distance in meters, we have our initial and final velocities in meters per second. Now please note that these terms are squared, so make sure that you square the 18 and square the 14, then subtract those values. Otherwise you're going to get the wrong answer. So I'm going to do, where I have more room, I'm going to do this over here. All right, and now it's a matter of just plugging it into our calculator. All right, and when I do so, I go ahead and get the value of negative 3,328 newtons. But we didn't want the direction because we're looking for the magnitude. This goes ahead and gives you a hint because it puts that in absolute values. So we're going to go ahead and put just the positive value. We do only need 2 sig figs, so this does round to 3,300 newtons. This next question is going to run a little bit similar to the last one we just talked about. So we are going to start the same process as normal. We have the, read the question, 70 kilogram bicyclist. We plus the 8.8 kilogram bike. And we are moving with an initial speed of 15 meters per second. We want to know how much work must be done by the brakes to bring the bike and rider to a stop. Right? So bike and rider says that we are going to add these two, so we get 78.8 kilograms. And we are coming to a stop, so our final velocity is 0. Right? We know that work is equal to a change in kinetic energy. So if I use the equation I just looked at before, we are looking at that work is equal to the 1/2 m VF squared minus VI squared. Right? So we have everything we need. We can go ahead and plug and chug. So the work is equal to 1/2 times 78.8 kilograms times 0 meters per second squared minus 15 meters per second squared, and that gives us some value in joules. So we already know this is going to be joules because it's work. What is one thing you already noticed without plugging anything into your calculator? Hopefully it's the fact that we're taking 0 minus something. So it's going to go ahead and give us a negative value. All right, and we do get 8,865 joules. We only get 2 sig figs here, so it's going to be 8,900. Right? Hopefully that puts you on the right track here. So that seems to be where we're having the biggest issue, is the work is equal to kinetic energy. This one, we are looking at the fact that any work can be related to any change in energy. Most typically we see it related to a change in kinetic energy, but we also have to do work in order to get a potential energy. In this particular case, we are seeing the fact that we are raising a bucket from the bottom of a well that's 12 meters deep, right? That means we are changing the potential energy of our bucket, right? So work is any change in energy. In this particular case, our work is equal to our change in potential energy, or that m times g times change in h, because we're not changing the mass of the gravity, we're just changing the height. And we were given that change in height. And we also know that power is equal to work divided by time. So we are looking at the fact that it's the mg delta h over t, or 5 kilograms times 9.81 meters per second squared times 12 meters divided by 15 seconds. All right, and we do get a power of 39.24 watts. All right, so we are looking at that particular one. We only get 2 sig figs, so we only get these 2 digits here. The number afterwards is less than 5, so we do not need to round up. So this is 39 watts. All right, this question we are looking at 4 forces and then do work. right? And we want to know which one has increasing power. So we're going to go largest power on this side, smallest power on this side. So power we know is work divided by time, right? And we're going to look at the fact that it's going to be joules per second. So we're taking this column and dividing it by this column. Let's actually zoom in further so we can see better. All right, so 5 divided by 10 is 0.5 watts. 3 divided by 5 is 0.6 watts. 6 divided by 18 is 0.33 repeating watts. And 25 divided by 125 is 0.2 watts. So we're ranking these from largest to smallest. So the largest one is going to go over here, and the largest number is B. So we're going to start with B. Right? The next largest one is A, followed by C and D. There were no two that were equal, so you would not have overlapped them. All right. Last question. Again, we're looking at that sort of change in kinetic energy is equal to work sort of idea. All right, so we're given the fact that we have a ball that has a mass of 0.14 kilograms. We're accelerating from rest, so our VI is 0 meters per second, and our VF is equal to 25.5 meters per second. And we're doing this in a time of 0.075 seconds. So we want to know how much work the pitcher does on the ball. Again, like I said, this is work is equal to a change in kinetic energy. Right, so work is equal to the 1/2 m VF squared minus 1/2 m VI squared. Our initial velocity is 0, so this term goes away. So our work is equal to 1/2 times 0.14 kilograms times 25.5 meters per second, and that term is squared. All right, when we plug that into our calculator, we do get 45.5175 joules. Right, and we only get 2 sig figs for our answer here. We are going to go ahead and round this up to 46. Okay. The next thing we're going to look at is the pitcher's power output. Power we know is equal to work divided by time. Well, we just found the work, and we have the time. Now, for part B, you do need to use your unrounded answer. Don't use your rounded answer, otherwise you're going to end up with some issues. All right, and we do get a power output of 606.9 watts. All right, we do know that's watts. We get 2 sig figs, so this does round to 610. All right. The last question is if we do it in less time. So this time we're looking at this equation, that power is equal to work divided by time. And as the denominator decreases, what happens to this power? Right? Well, as this gets smaller, this number has to get bigger. All right? So the power is going to be more. Hopefully that puts you on the right track. If you have any additional issues, please feel free to email me, and I will be more than happy to record more videos.